Hey everyone, and welcome back to our electronics tutorial series. My name is Aaron from AX Electronic, and today we are going to be looking at some of the different types of diodes. So I mentioned before that the PN diode is more of a general purpose type of diode, probably the most common, but there are still other types that I think you guys should know about. So we're going to talk about a few of those. We're also going to talk about some of their applications, where they're used at, and how they're useful, what makes them so special and different. So let's go ahead and jump right in. So this is the diode that we are very familiar with, the PN diode, and its symbol, if I were to draw it, is just that triangle and the bar, like we've seen before. Okay, so this is definitely the most commonly used diode, most general purpose diode, also the cheapest. Okay, so it's the very easiest to manufacture, so it's definitely one of the cheaper ones and more common ones. So its nominal forward voltage is about 0.7 volts. That can vary depending on, the material, the fabrication process, and things like that. But 0.7 volts is a good approximation for it. Now, what's very good about these guys is that they can have a pretty high reverse voltage before being destroyed. So if you remember our full bridge rectifier from before, that has to withstand reverse voltages of up to 120 volts, okay? So, up to 170 volts. 120 volts is the RMS. So up to 170 volts. And if it's a weak diode, it could very easily enter breakdown, start letting current conduct, which is not good, okay? So a PN diode is a pretty good, robust diode for withstanding those voltages. That's not to say that every PN diode is built the same and can all withstand the same reverse voltage, but that they are generally stronger compared to some other types of diodes. So PN diodes are good for general purpose uses if you need a little bit higher of a reverse voltage breakdown limit. Now, this is one of the new diodes that we've looked at. So this is the Schottky diode, okay? And it looks like this. So if I were to draw it, still that same triangle, except now I would have this little thing here, okay? So I'm not very good about drawing them, but that's what a Schottky diode would look like if I was drawing it on a schematic, okay? Now, the main benefit of a Schottky diode is that it has a smaller voltage drop, okay? So the PN diode, remember, had 0.7 volts. And this guy is only going to have 0.3 to 0.4 volts. Usually 0.35 volts is a good approximation if you're working on these circuits. Now, in addition, they also have what's called a faster recovery time for high frequency circuits. And the reason for that is because diodes, whenever they are reverse biased, they actually have a little bit of capacitance in series. Okay, so whenever they're reverse biased, you're actually charging up this capacitor a little bit. So for high frequency AC circuits, this is getting charged and discharged very quickly. So if you want to block a voltage, you need to have a very quick recovery time. In the same way, if you want to let current flow, you have to have a really quick recovery time. And PN diodes can be a little bit slow when it comes to that, but Schottky diodes have a smaller capacitance. And because of that, that makes them really good for maybe higher speed circuits. So if you need something like maybe even a high frequency RF circuit, or maybe if you're working in this kilohertz range, these diodes might be a little bit better. Now, their disadvantage is that they do have a little bit weaker reverse breakdown voltage, okay? And again, that's going to kind of come as a trade-off. Because you have that lower voltage drop in the forward direction, you're going to not be able to withstand as much of a reverse voltage before it starts to break down and starts to conduct. And in addition, because the fabrication process is a little bit different and more involved, they are going to be more expensive compared to your general purpose PN diodes. It's not to say that they're very expensive, but they just are more expensive. So if you're working on a very complex PCB or something like that, and you have a lot of diodes, those costs are definitely going to add up, especially if you're talking about production. So it is something to consider, although it's not too big of a deal if you're just a maker or a student. Now, up next is the Zener diode. Now, Zener diode, if I were to draw it out, it'd be that same triangle and then a little bend like this, okay? And it is important that you're separating these different types of diodes because they are used for different things. Now, a Zener diode in the forward direction behaves pretty much the same as a normal diode. It's going to have this 0.7 volt drop, and it's going to let current flow in that direction. What makes it different, though, is that it does have a very well-controlled reverse breakdown voltage. So if you remember our PN diode, we have, for our IV curve, if this is V and this is I, we have it look something like this, and we want it to go very far out before it starts breaking down. Okay? But for our Zener diode, in the forward direction, they're going to work in that same way. So if this is V and this is I, but in the reverse direction, it might only be something like 5 volts. Okay, so at 5 volts, it's going to start conducting in the reverse direction. Now you might ask, why is this useful? We want something that's strong and robust. We want it to be able to resist those reverse currents. There are actually some instances where you would really like this. So I'm going to give you one example. So let's suppose that you have your Arduino here. Let's just do ARD for Arduino. And you are going to give it power to its 5-volt input. Okay, so you've got maybe something downstream that's providing 5 volts to it. So you want to have 5 volts right here. So let's say maybe you've got a battery, and this is providing 5 volts. Everything is working just perfect right now. But let's suppose that you set it down for a couple of days and you don't remember what type of battery you're supposed to have here. So instead of that 5-volt battery, you mess up and you apply a 9-volt battery. Well, that's not very good, because if you apply 9 volts to a 5-volt pin, especially on a microcontroller, that could cause this thing to break pretty easily. So what you can do is that you can actually use a Zener diode right here and make sure that it is a 5-volt Zener. And what that means is that whenever it has something that is more than 5 volts, so if we try and apply this 9 volts here, it's going to short circuit and a lot of current is going to flow through it all at once. So whenever a lot of current is flowing through a battery, that's actually going to drop its voltage. And especially if it's a different type of supply that maybe can't provide as much current, it's again going to cause it to drop its voltage until it reaches 5 volts, at which point it'll stop conducting. So it reaches that stable point whenever it is at its Zener rating. So like I said, this is useful as a voltage regulator. If the voltage is going to get too high, it's going to do what's called clamping. It's going to clamp that voltage to a certain predefined value. So in this case for the Arduino, if we have that 9 volts there, it's going to drop that to 5 volts to make sure that we're not going to break any components. So this is really good if you know that there's a current limit to some component that you don't want to go over. So maybe if it's something like a transistor that you don't want to accidentally break, you can include a Zener diode there to make sure that that voltage does not go above some specific value. Okay, so these guys are actually really useful in the forward or in the reverse direction. In the forward direction, they act like just a normal diode. You could use them if you wanted to, except they're going to have that Zener breakdown, which may not be desirable for your case. Okay, Varactor diodes. These are pretty cool, especially for my area of interest, which is RF circuits. So Varactor diodes just look like this triangle with a capacitor added to it right at the very end, okay? Now, you might remember here, we were talking about the Schottky diodes. Every single diode has a little bit of capacitance in the reverse direction. Now, what I did mention is that as you increase this reverse voltage, so if this gets to maybe 10 volts, that capacitance is actually going to change. And that's just due to the physics involved with these devices. So that capacitance is going to change just a little bit. Now, in most diodes, we don't want it to change too much because then that could cause some weird second-order effects that we don't really like. But for a Varactor diode, it's designed to change as much as possible. So Varactor diodes are typically aren't used in their forward direction. They're used exclusively in the reverse direction as kind of a voltage-controlled capacitor. So let's say that we have a Varactor diode connected to ground, and we have some voltage on it right here. So this is our control. So if we start off with maybe 2 volts, maybe this guy has a capacitance of 10 picofarads. But then if we increase to 5 volts, it might go all the way up to 15 picofarads. Now, one application of this is in something called a voltage-controlled oscillator. So if you remember back from our op-amps video, oscillators are used to create either some sort of periodic waveform, usually a sinusoid. And that's actually really important for radio frequency circuits because we need high-frequency sinusoids to carry and modulate our signals and send them out into the world for everybody to hear. So we have to be able to create these high-frequency sinusoids, and we also have to be able to vary them. Okay, so a lot of radios, especially like the FM radio that might be in your car, have a very wide range of stations that it can listen to. Same way radios that are transmitting want to have a wide range of spaces that they can transmit to. You don't want to have just a single transmit frequency on your radio. So to get around this, they use voltage-controlled oscillators. So what they'll do is that they can change this control voltage, which will change the capacitance, which ends up having the effect of changing the frequency that it's transmitting on, which is super important and very awesome, something that is really, really good to use, especially for radio frequency circuits. So I just wanted to mention this one because I do think that it's important to understand that these diodes do have a capacitance and that we can actually use these capacitance. So if you see a Varactor diode, especially in a maybe radio frequency circuit, you know that it might be pointing you toward a voltage-controlled oscillator, or at least maybe something that changes with that change in capacitance. Now this last one is probably the most common that we've probably all seen and definitely heard about. So this last one is a light emitting diode, also called LED. So the symbol for this one just looks like a normal diode, or a normal PN diode, with a little arrow coming off of it, or some people do a little lightning bolt arrow like that. Okay? So this just shows that this is a light emitting diode. So it looks like a normal diode, so just a normal diode with some light coming off of it. So it's all in the name, light emitting diode. Probably the most used or most commonly used diode for things like indication. I mean, if you have a circuit board, you want to know when something's going wrong, shine a light, things like that. So they're used pretty common in practice. For microcontrollers especially, or people just getting into electronics, usually blinking an LED is one of the first things that they end up doing. Okay, so by applying this forward voltage, you can actually create some light. Now, the forward voltage for these guys can vary depending on the type of diode that they are, the type of light that they're going to emit. So some of them could be maybe something like 3 volts. So it definitely is a whole lot higher. It could be 2, 3 volts, maybe even 5 volts, okay? So it is definitely a whole lot higher, but that's because we're having to create this light energy, okay? So we're working to create some energy, so we're going to have to add a little bit more energy into our circuits, okay? Now, in the reverse direction, so if we apply a voltage to our light emitting diode, and we let current flow in this direction, then light will come off. But if we try to apply a reverse current, then it's going to work just like a normal diode, and it's going to block this current, and no light's going to come out because there's no current flowing, so there's no energy being expended. So if we try and apply current in the reverse direction, or don't apply a forward voltage, then that LED is going to be off. But if we do apply high enough forward voltage, that LED is going to turn on. Now, these lights don't specifically make, whatever red, yellow color it is, but they do make a certain wavelength of light. And then their bulbs are actually surrounded by a phosphor coating. So that phosphor coating reacts with the wavelength that is being emitted, and that actually expands, or not expands, but it actually emits a different visible frequency of light. So that phosphor coating can actually produce all the different colors that we see. So things like red, yellow, blue, green, those are all changed only by that phosphor coating. They've got that same stuff deep down inside. All right, so this is a nice introduction to all the different types of diodes that we have. There are definitely quite a few, and there's definitely more that I have not mentioned here, but these are some of the more common ones, and the ones that I feel everyone should be introduced to at the very beginning, just so they can keep them in the back of their mind. So if you guys have any questions, please leave them in the comments below. If you like this content, please give me a thumbs up and subscribe for more. Otherwise, thank you guys for watching, and I'll see you next time.